Welcome to my online lecture on Chapter 28 and Chapter 29. Chapter 28 topics that were not covered so far are paramagnetism and diamagnetism, as well as ferromagnetism, which is the strongest type of magnetism. So, if you're used to seeing magnets which are made out of iron, cobalt, nickel, those materials exhibit ferromagnetism. But other metals experience paramagnetism and diamagnetism when subject to a magnetic field. So we're going to talk about what those things are. Paramagnetism actually generates a field that adds to the external field, whereas diamagnetism opposes the external field. And what we're going to learn is that each of these effects are due to electron behavior. So remember in Chapter 27 we talked about magnetic moment. So an object's magnetic moment was a way of quantifying the torque it experiences in a magnetic field. So remember that we define this magnetic moment vector as the current times the area or cross section, pointing in the direction shown in the picture, placing your fingers in the direction of current, curling them around the current direction. Your thumb gives you the direction of the mu vector. So notice that if we were to align two objects that are flowing current so that their magnetic moments are aligned, also their magnetic fields would be aligned. Because if you place your thumb in the direction of current, field lines trace circular patterns around the wire. So these two objects shown, their magnetic moments are aligned and their magnetic fields are aligned. So there's a few different electron properties that we want to talk about. The first one is that electrons, as they orbit the nucleus of atoms, will behave as a current around a wire, so a current loop. So what you see here is an electron orbiting with speed v, and as you can see, the current goes in the opposite direction because this is a negative particle. And we can see the associated mu vector. So place your fingers in the direction of the current and you'll see why the mu vector points the way that it does. So electrons actually behave as tiny magnets. So in addition to orbiting the nucleus, each electron has a property called its magnetic spin. And that's, kind of think about that as the electron rotating around about its own axis. Although it's much more detailed than that, but for our purposes we'll consider that the magnetic spin. And this means that an electron is actually a magnet. In most substances or certain substances, electrons will be paired, spin up and spin down. So these magnetic moments will cancel each other in that case. But some materials have unpaired electrons, in which case we're going to have the effect of these unpaired electrons' mu vectors behaving like current loops. When we have paired electrons, the picture on the right-hand side here shows that their magnetic fields will cancel each other. So what causes paramagnetism and diamagnetism? Well, three principal sources: the electron's spin, the electron's orbital angular momentum that we showed on the last slide, and changes in that orbital moment induced by an applied magnetic field. So when we hear induced, what we're seeing is Chapter 29 topics, electromagnetic induction, where a current will be induced to oppose the change in magnetic field. The first two sources give us paramagnetic contributions. The last source, electromagnetic induction type source, gives us a diamagnetic contribution, or it opposes any field that's brought near. So we can define the magnetization vector, m, as for a bulk material such as a block of metal, the sum of all of the magnetic moments per unit volume in that material. So we take all of the individual electrons' mu vectors and we add them up as a vector sum across the entire volume and then divide by the volume. And we get m. So what this does is it describes how this material adds to or even subtracts from an applied magnetic field. Well, why do we want to do this? Well, because some of the electronic devices that we're using uh, consist of coils of wire around an iron core like this. In this case, the iron core is going to add to the magnetic field. So on the left-hand side, we have a bar of iron, and that bar of iron may be demagnetized in the beginning, and then the coil of wire begins to flow current, and then that causes magnetism in the bar, and then that field adds to it as shown. So we're left with the equation total magnetic field equals initial field due to the coil plus mu sub 0 times m, where mu sub 0 is the magnetic permeability of a vacuum. So if we have magnetic fields in a non-vacuum, such as in a bar of iron, we can define the relative permeability, K sub m. This is very similar to the idea of the dielectric constant. So remember, we defined K, the dielectric constant, and we had epsilon is equal to K epsilon sub 0 for each material. Well, here we have mu is equal to K sub m mu sub 0. So see below the definition of K sub m. And now we're going to also define the magnetic susceptibility, X sub m, which is nothing more than K sub m minus 1. The reason we do this is because X sub m now greater than 0 will give us paramagnetic substances, and X sub m less than 0 gives us diamagnetic substances. And the table shown gives you an idea of what substances add to the magnetic field, which are ones on the left-hand side, and which substances subtract from the magnetic field, which are substances on the right-hand side. And we're going to see this actually in lab this week. Ferromagnetism occurs in iron, cobalt, nickel. And actually the way that these substances behave is electron spins align in tiny domains. These domains can be on the order of a centimeter, 2 centimeters across. And in that domain, basically if you were to consider only that domain, it would act as a tiny magnet. However, as you can see on the left-hand side, all of these domains are aligned in different ways in a demagnetized piece of iron. And then once that iron is brought into a magnetic field, you get the picture on the right, where all of these domains tend to align with the field. And at that point, that bar of iron or nickel or cobalt is magnetized and behaves as a magnet. Now we talk about hysteresis, which defines how a magnetic field can be stored in a substance. So read about hysteresis in chapter 28 and understand it. And then we also talk about the Curie temperature. So magnetic materials, ferromagnetic materials, can be heated to a certain temperature where they'll actually demagnetize. One of the other things you could do to demagnetize materials is to drop it onto the floor or jolt a material, which can cause these domains to become misaligned and demagnetized. So we can create electromagnets now, which are, again, iron core surrounded by a coil of wire. And because iron is one of these substances that has a strong magnetization, ferromagnetic substance, it greatly adds to the magnetic field strength. This leads us to chapter 29, electromagnetic induction. So we've seen this already in Professor Tronin's class. Magnetic flux, which we can think of as a flow of magnetic field through an area. The idea is similar to electric flux, similar to water flowing through a pipe. So the relative strength of that water flowing through the pipe can be thought of as velocity times area. So larger area gives you greater strength. Higher velocity gives you greater strength. Here we have magnetic flux equal to B dot A. We've seen this before with electric flux. The units of magnetic flux are Webers, Tesla meters squared. So why do we want to talk about magnetic flux? Well, it's because of Faraday's law of induction. So these are observed quantities based on many experiments that an EMF will be generated in a coil of wire based on the changing magnetic flux over time. And so this EMF is an electromotive force, or potential difference if you have terminals, and you would see it on a multimeter if you had the wires connected to a terminal of the multimeter as shown. EMF is equal to negative d phi dt for one turn. With multiple coils of wire, we have EMF is equal to negative n, or the number of turns, d phi dt. So this is really interesting. We have a changing magnetic field giving rise to an electric field. And we learned earlier that if we have a changing electric field, that gives rise to a magnetic field. So the two of these phenomenon are going to be combined in chapter 32 and give rise to electromagnetic waves. Lenz's law talks about the direction of the induced current. So it's very important to understand this right-hand rule and how we do these problems. So basically, Lenz's law says that an induced current will tend to oppose the change in magnetic flux. Even if the loop doesn't form a complete circuit, we're going to have an induced current in that loop. And the induced EMF is going to be opposite the change in flux. So here's example 1. Let's talk about what is the direction of current flow induced in these loops. So part A shows a magnet being brought into the page through this circular area. So what we're doing is we're increasing magnetic flux into the page. Therefore, an induced current will oppose that by decreasing magnetic flux into the page. How do we do that? By increasing magnetic flux out of the page. So using a counterclockwise current will give us a magnetic flux out of the page. So this is going to be an induced counterclockwise current. Question B, this shows a magnet being passed through the cross-sectional area at a 90-degree angle to that area vector. So as we can see here, since flux is B dot A, this is B times A times cosine 90, which would give us 0. So there's no change in flux, no induced current. Part C, we pull this loop to the right out of the magnetic field. So we initially had magnetic flux going out of the page. The induced current is going to tend to increase magnetic flux out of the page to counteract. So again, we're left with a counterclockwise induced current. Part D shows shrinking a loop in a magnetic field. We had magnetic flux into the page, we're decreasing it. So the induced current is going to increase magnetic flux into the page. So we have a clockwise current. Hopefully these make sense. If not, please pause the presentation and go through these on your own. Also, you can look up online and find many, many examples of Lenz's law and practice using this right-hand rule. Now we're going to get into a numeric example. So we're given a coil of wire, 100 ohms, 100 turns. Okay, so we're going to be dealing with N. This is pulled uniformly out of a uniform magnetic field as shown. So constant speed removed from this field. So we start out with a magnetic flux greater than 0 into the page as shown. And then we're left with a magnetic flux of 0. So we do have d phi dt. The elapsed time is given as 0.1 seconds for this loop to be completely immersed and then completely removed. Please answer the following. What is the value of the induced EMF? how much induced current flows around the loop, how much force is required. So why would we require a force to pull this loop out of the field? Because if we look at this loop, we have a current, induced current, moving in an external magnetic field. And that means that we have induced current in the left-hand side of this loop that will generate a force based on the equation in chapter 27. Force is equal to IL cross B. On the top and bottom we'll also have forces, but those forces will counteract one another as shown, because whatever the induced current is, it's going to move in opposite directions on top and bottom. First of all, how do we tell what the induced current direction is? Well, we initially had magnetic flux going into the page. What we're doing is decreasing that. So the induced current is going to tend to increase magnetic flux into the page. And so a clockwise current will increase magnetic flux into the page. So with a clockwise current, taking a look at the left-hand side of this loop, we have I going upward, cross B going inward, gives us F sub m as shown to the left. So we need to apply an external force to counteract that. Question C is asking how much is that force. For one turn we have magnetic flux B dot A. Here it's equal to B times A because the magnetic field makes a 90-degree angle. Actually, excuse me, makes a 0-degree angle with the area vector. Area is calculated as 5 centimeters, that quantity squared. For one turn then, the magnetic flux is 0.6 Tesla times 0.0025 meters squared, giving us 0.0015 Tesla meters squared, or Webers. Now we can calculate induced EMF because we have the equation EMF is equal to negative N d phi dt. Now the negative sign is just simply to show that this EMF counteracts the change in flux. Nothing more. And that's approximately equal to the delta phi delta t. And that's where the trick to solving this problem lies, in taking that d phi dt and turning it into a delta phi delta t. We can do this for short time intervals. When we plug in all of these intervals, we get negative 100 turns times final flux minus initial flux over final time minus initial time, giving us 1.5 volts induced EMF. Now to solve for the induced current, we can use Ohm's law because V is equal to IR. This gives us an induced current of 0.015 amps. So this answers parts A and B of this problem. Now using F is equal to IL cross B, here F is equal to ILB, where I is the induced current, L is 5 centimeters, B is 0.6 Tesla. Plugging these in gives us a force required to move this at a constant speed of 4.5 times 10 to the 4 newtons. Okay, now that we've talked about magnetic flux, what it is, and the fact that changing magnetic flux will induce an EMF, we're going to talk about 3 different ways to change the magnetic flux. Now, it's interesting that there are devices that you see in everyday life that are based on each one of these 3 ways to change the flux and function accordingly. If we can change magnetic field strength, we can change magnetic flux and induce an EMF. So we have a dB dt, change in field. If we can change area through which the magnetic field passes, then we can change flux, d phi dt. So we have a dA dt. If we can change angle between A and B, we have changing flux. This is d theta dt. So actually an electric generator is based on d theta dt. We rotate a coil of wire in a magnetic field, which in turn changes the direction in which the coil faces the field and induces an EMF. If we have some combination of these three things as well, we can change magnetic flux. So the next concept we talk about is a motional EMF. Not emotional EMF, we're not going to cry. We're talking about motional EMF. So the idea here is changing cross-sectional area through which the magnetic field passes, and then inducing a current. So here we see the rectangle that's made up of the rails, so to speak, on the left-hand side, and the bar which can slide along those rails at some speed. We can see that as we move that bar to the right, let's say along the positive x-axis to the right, we're increasing cross-sectional area, we're increasing flux out of the page, so we're going to end up with a clockwise current to increase flux into the page. And that's why the positive is shown on the bottom, negative is shown on the right. If you were to take a multimeter, place it across these terminals, across this bar, you would find a DC voltage potential difference once you started sliding that bar. So this is a really interesting device. Has many practical applications, including the concept of a railgun, which we'll go through in class. So we're inducing an EMF. Change in flux is proportional to the change in area. Or the rate change in flux then is also proportional to the rate change in area. So we have EMF equal to d phi dt, which is dB dot A dt. But here the magnetic field makes a 0 degree angle with the area. So B dot A becomes B times. But we notice that B is a constant here, a constant uniform field, so we can pull this out of the differential, and we're left with the equation induced EMF equal to B dA dt. But we can calculate our dA dt as the change in area. Area is L times x, whatever x is, the position of this bar. So what we're really interested in is L times dx dt for changing area, since L is a constant. What is dx dt though? Dx is v, or speed, nu. We talk about the Greek letter nu. And so that's the equation for motional EMF for solving problems like this. You'll see examples of these in the homework. Okay, so now we're going to go through the example. So given that the length here is 0.25 meters, and that we have a uniform magnetic field out of the page, strength is 0.2 Tesla, and that this bar is pulled at a constant speed to the right of half a meter per second. Determine what the value of the induced potential difference or induced EMF across the terminals will be. So this is as simple as plugging values into the equation. 0.2 Tesla, L is given as 0.25 meters, speed is given as half a meter per second. When we calculate this, we get 0.025 volts. So please go through all of the examples in this presentation, check your units, make sure that all the units make sense. This will help you on an exam. And thank you for watching the presentation.